Hello, uh, welcome to session number 28 in the series Analog Integrated Circuit Design using ADS. My name is Anurag Nigam, and continuing in the section of analog PLL design, which I give an overview in session 27. I'm going to design the first block in fractional NPLL, that is multi-modulus frequency divider, right? So I am going to introduce you to as much of the process as is required, not all the details of a process. So this is a 130 nanometer SIGE process, and we have got, okay, so this is the back end of the line, and I'm not going to go into details of various layout rules because that is going to be part of layout when we do that. There are 5 metal layers which are 540 nanometer each, and then there are 2 thick metal layers. One is 2 micron, other is 3 micron. Other than that, this is an anvil process, and you have an opportunity to make an insulated NMOS device using a PUL, but I'm not going to cover that. I'm just going to take this as an NVEL process with a PMOS device in the NVEL and an NMOS device sitting in the substrate. Now below the all the metallization, the substrate goes like this, that there is a epi layer which is a slightly slight implant so that its uh, conductivity is 20 ohm per square, right? While what's below that is a silicon which is 750 micron, it says here, but then it is 100 micron after thinning, right? So that various thinning options are possible here, right? So without going into details of what this process is, let's go into devices which we are going to use for simulation. So there is a NMOS device, and then there is a PMOS device. NMOS device, the minimum channel width can be 0.15 micron, while the maximum length for maximum width per finger is going to be 10 micron, and the length of the device can be 130 nanometer to 10 micrometer. We are going to use the minimum feature size for the speed. Then there are a number of fingers which can be from 1 to 100, unless it is a RF NMOS device which sits surrounded by uh, a p-tap region, right? So for isolation, so there's going to be only 40 fingers in that. Maximum for fingers is 40. Same thing is there for PMOS device. uh, the width of a finger can vary from 0.5 micron to 10 micron, and then there can be 1 to 100 fingers, and the length can vary from 130 microns to 130 nanometer to 10 micron. Again, we are going to use just a NMOS device, not a RF version of it. In RF version, you have got N-tap around the PMOS in the well, and it can only support up to 40 fingers. Now the next thing is that we are not going to use multiplicity of the device. We are going to use the number of fingers, number of gate fingers, NG, right? So this said, apart from that, there is a high voltage device also available, and there are bipolar devices available. Okay, so there are singular devices, or there are two ammeter finger devices, right? So that we will cover when we use bipolar device. uh, Now in case of substrates, the contacts are established using beta 1 and n-tap 1. Okay, so beta 1 is for the NMOS device, and there is going to be a global node called subbang. Bang means exclamation mark, and it points to a global node, right? So a global node can be a substrate ground, and then you can have a device ground, right? So in between you have to put beta 1. Then for a PMOS device, you have NTAP, which is basically the contacts within the NVAL, and they can be connected to uh, the supply. Okay, so basically if you cascade if you have one on top of the other, PMOS, then the source and the body can be shorted through this tap. Now uh, this, for digital purposes, you can directly short the source to the body, in case of a PMOS, but the body terminal for NMOS will go to the least negative terminal, right? Because it sits in the substrate itself. Now, besides that, there is a variable capacitance which we are going to use when we do a VCO design, right? So that's just for information is there. Then all the layouts are on a grid of for this 130 nanometer, they are going to be on a grid of 5 nanometer. So what you have to do is first we create a new workspace, and I'm going to call it as phase lock loop. Let me give a full name, phase lock loop, correct? And here I have to attach the libraries. So you have to attach, if you don't find it here, you have to browse to that library .lib file, right? And once you do that, you have to specify the resolution of the substrate for the layouts, which here shows as 1 nanometer, right? So it has to be 5 nanometer. So I'm going to adjust this when I do the layout. It's a finish. Once you do that, you have a blank workspace, and I'm going to start designing the multi-modulus frequency divider. So for that, first thing I'm going to do is I am going to generate transmission gates. So if you want to study about transmission gates, there is another playlist which I have under the name Digital Circuit Design, and you can refer to those tutorials to see what these designs are. Transmission gates. Okay. So the key block in the transmission gate is called transmission cell. So I'll call this as a TX cell. Right. Okay. Now one thing is there is if I'm going to use an NMOS device and a PMOS device. So there's an NMOS device here, and the substrate is always at a known potential, and in the pass transistor it's going to be the input as a known potential node. So I'm going to put substrate on the left side, the source on the left side, right? So that's your NMOS device, right? And here let's see, grid is not going to. So what you have to do is you have to go to not snap grid, you have to go to preferences, and don't worry about this warning. What I'm going to do is I'm going to enable snap to the pin. Also I'm going to have this 0, 6 to 5, correct, and say apply and save a copy as the schematic preference file. So now everything is going to look fine. Okay, so now here I have an NMOS device and sizing it. So this can go up to, one finger can go up to 10 micron, but let's say, okay, hang on a second, one finger can go up to 10 micron. Okay, so let's say I want 2 fingers on a 5 micron device, right? So let's say number of fingers is here, so I want 2 fingers, and I want a 5 micron device. So each finger is 2.5 micron, total is going to be 5 micron, length is 130 nanometers. Fine, done. So now the next is I want a PMOS device. So this also I'm going to rotate. The source is on the left hand side, right? And here I'm going to take the same way. I'm going to take this as 10 micron, and here I'm going to put 6 gates and total of 15 microns. 15 microns, yeah. So each gate is 2.5 microns, and this total width is 15 microns, length is 130 nanometer. So I have got 2 of these. Now this PMOS device is going to have an N-tap connection to supply. So I am going to put N-tap 1. Okay, so the valve basically is going to be tied to the body here, and then the tie is going to be to the supply, right? So I'm going to put in here a pin which is VDD, and that's the supply. Okay, so PMOS is taken care of. Now for the NMOS, I can directly give here a sub. So I can go here and call this as a global node, small, all small subbang. Okay, so now this is going to the subbang, right? And the ground is not there because this is a pass transistor, right? So there is no ground here. Okay, so now we are done with this. Let me just put this on the top. Okay, so we are going to have an input A and the output Q, and then we are going to have C, which is going to control the, C is going to control your NMOS device, and the NMOS device passes a 0 from A to Q. So this is for passing state 0. And for passing state 1 from A to Q, you need a PMOS device. So there will be a C bar because PMOS is an active low switch. So this will be a C bar. Okay, so now you have got a transmission cell. Now what I'm going to do is I'm going to make a symbol for this transmission cell, right? And I want to have a very small symbol so that later the diagrams look pretty. Okay, so I'm going to choose medium, and I'm going to choose it this way, that this is a square, and this is A, this is Q, and then this is C, and this I'm going to move over here, and then I'm going to have C bar. So this is going to be C bar. Again, I'm going to move this over here, and then I have VDD. So I'm going to rotate this, and again I'm going to move this over here, and I'm going to connect this over here like this. Now to remind me that I have a bar terminal here, I'm going to put a small bubble here. Okay, so to put a small bubble, I'm going to create some space for it and make a small bubble, which I'm going to put over here. Maybe I can make it slightly bigger. Okay, so that's the bubble. So that's the symbol for a transmission cell. Now once I have a transmission cell, I would also need a mux. Also, I'm going to make a mux 2 to 1. Okay, one more thing I want to check is if I'm recording. So I'm recording. Okay, so to make a mux, all I need is a transmission cell. So just one more thing, snap enabled. Hang on a second. Snap options are enabled. Okay, so I need to put in a cell here. So one path is this, the other path which is in tandem is over here. So for a 2:1 mux, as the output can be high impedance state, I can combine the outputs. And this is when you have tri-state devices that you can combine the output, not with the gates. Okay, so you have to keep that in mind. So now this mux, right? Okay, so now I'm going to put in, I need also a NOT gate, so I am going to make another folder for static gates. Okay, and in the static gates, first thing I'm going to do is make a new schematic and call it a NOT gate. Okay, so that's a NOT gate, and I'm going to use the same devices as in the transmission cell, a PMOS and an NMOS with the sub tab and this. So I'm just going to copy this over here, and I'm going to paste it over here. So I'm going to rotate them later on. Okay, so I want to make an inverter. So this is an NMOS device. Let's rotate this. Okay, so I don't want the sub to go away. So that's a sub bang node. And then this is a PMOS device. I'm going to rotate this. Oh, okay, fine. So here's a PMOS device with its tab like this. Correct. And this is connected over here. And this is my inverter and this is a ground. Okay, so now I'm going to put the pins. So I have got A, and then I've got Q, okay, and then I have VDD. So this one is not required. So I have a VDD, right? So that's a VDD terminal, and then I have a ground, correct? So I have a ground. So there you go. There you have a ground. Okay, so this is a NMOS. Sorry, this is a inverter. So I'm going to make a symbol for that inverter. Symbol. Okay, again, I want to make it small so that, you know, later on I have a cute schematic. Okay, so that's that. And I have A as the input. I have Q as the output. I have VDD, which is over here. And this I'm going to move here. And then I have a ground, which is over here. And this terminal name I'm going to move here. And then I'm going to put a bubble to remind me that the output is inverted. So I'm going to create the space for a bubble, and I'm going to insert a small bubble, right? So that bubble goes in here. It's kind of big, so let's move this to the left a little. Okay, that's good enough. And Q I'm going to move in. Okay, so this is the symbol for inverter. Now the next thing is I want select, right? So that select line S0. So that select line basically controls C, or gating, right? And then I need an inverter following that. And this is controlling this. So if S is low, then this path is through. So I will call this as I0. Okay, so I am going to have other things like VDD. And then I'm going to have ground. Okay, so VDD and ground pins. and I'm going to make the connection by naming them. So this would be VDD, this is VDD, this is VDD, this is VDD, and this one is ground, and this one is ground. And then you have got output Q. So that's the output Q. And then I have I0. So if S is 0, then this path is through. Okay, so another thing is, let's connect this completely. So this is controlling that. Correct? So I have got I0, which is over here, that goes through, or I have got I1, which is over here, so I1 goes through. So if S0 is 1, then this path is through. That means I1 goes through. Okay, so this is a mux. So I am going to just make a small symbol for mux. Okay, new symbol, create symbol. Okay, again I want to keep it clean, so I'm going to rotate this. So this is your S0, and hang on a second. Okay, so I'm going to make a signal for a mux. Small judgment. Okay, so that's a Q. Okay, somehow I need to extend it, or what? Q is not finding the center. Okay, now everything is symmetric. This is S0, which is over here, and then you have got VDD, which I'm going to put over here. So that's your VDD to the mux, and then you have the ground. So that is the ground terminal, and I'm going to do something here to make it look okay. So this is your ground terminal, this is your S0, and turn back the grid on. Okay, so this is my symbol for a mux. Okay, so for a 2x3 cell, I need a mux, and I also need an AND gate. So I am going to make an AND gate over here. New schematic, AND gate. Right, let me see if I'm recording. Okay, 24 minutes. So I am going to make an AND gate using a mux. Okay, so that's very simple. Over here, so when A is high, so A is basically controlling the select signal. When A is low, 0 goes through. That means that this node is going to be ground. So ground, so 0 goes through. Then I need a ground here, ground pin. and I will call this as ground. Okay, and when A is high, then B goes through. So there's a terminal B here, correct? So that terminal B goes through. And then you have got VDD and ground, right? So let's name this as ground and name this one as VDD and introduce a pin called VDD and name this as VDD. Okay, and then you have to just connect another pin which is Q, which is the output. Okay, so that's your AND gate. So I am going to make a symbol for an AND gate. New symbol. Okay, again I want this to be small. So all I need is a symmetric view here. Up to here. And this can disappear, this can disappear. And yeah, so let me get this like this. It has to be just symmetric. And okay, and this is a AND gate. This is not an AND gate. So that's VDD. And that's a ground. So that's an AND gate symbol. Done. So now I'm going to make PLL components. So I'm going to make a new folder, MMFD, or multi-modulus frequency divider. In this, I'm going to first make a new schematic called cell 2 by 3. Okay, create schematic cell 2 by 3. Okay, so for this, all I need is a D latch. So I can make a D latch using transmission cells. So let's start here. F5. And I want the clock to be differential, so I'm going to give 2 pins. One is going to be called clock, and the other one is going to be called clock bar. Correct? And I'm going to name them. So this is a small clock, and this is a small clock B. Done. So this basically is clock B, and this is clock. So this path is through when clock is high. This is the master, right? So then I have another this thing which I will call as VDD as the supply. Correct? So that's VDD. Okay, and name this as VDD. And then this is also VDD. So we have a through path which is going to be AND gated. So I'm going to put in an AND gate here. So this is an AND gated through path. F5. Okay, I guess this is easy to follow. And this supply is VDD. And this is a ground net. Okay, now I need to hold, when clock is low, I need to hold the output. So I would just copy this, and to hold the output I need positive feedback, right? So that positive feedback will be in tandem with the input. So this is going to be clock B, and this is going to be clock. So now this is in tandem. And F5. Okay, so now this path is going to be a feedback loop. So I need a NOT gate, 2 NOT gates, static gates. So I need 1 NOT gate, 2 NOT gate. and here are the NOT gates. Again, I'm going to have VDD and grounds. So this is going to be VDD, this is going to be VDD, and this is going to be ground, and this is going to be ground. Correct. And this is a feedback path. So that's a feedback path. Okay, so now when the clock is high, the path goes through. When the clock is low, then the output is held constant with the help of this feedback path. So this is master, and then I'm going to have a slave. So the slave is going to operate in tandem again. So that's a slave. So I have to change this. So this one is going to be clock B. It didn't happen. So this one is going to be clock B. Apply and close. And this is going to be clock. Cancel. So this is in tandem. Apply and close. And here, this is going to be clock. Apply and close. And this is going to be clock B. So master and slave are in tandem. So that's very simple to understand. Okay, so now this forms, so if I take a NOT output, so this is going to be that which is going to be fed back in. Okay, and so basically this is going to be your Q bar, and this is going to be your Q, isn't it? Okay, so this is going to be your Q bar. Sorry. So that's your Q bar. And if I pick before it, or I can pick after it, so that will be Q. So now everything is going to be on the falling edge. The transitions are going to be on the falling edge. Right? So let's make this as Q, because this would be slightly degraded. And let's make this as a Q bar. It really doesn't matter. Okay, so that's your Q bar. So this comprises a T flip-flop. So if I have this input as high, then this will toggle. Right, now I don't want it to toggle freely. I want the toggle to be under control. So the best way to do this is take this and establish another path. So I am going to take this and establish another path here, which I am going to break over here. Okay, so I'm breaking that path over here. Okay, so now I'm going to AND gate them. So I need an AND gate, which is the same thing, which I am going to rotate and place here. Okay, so now this goes in this path, and this is called mod in. So this is for cascading. This is for cascading your 2x3 cells. Mod in, modulation in. So that's mod in. And then I need another one, AND gate, over here. And this would have a control bit P. So that's a control bit P. And then this is also mod out. So this is for cascading. So I'll create another. Okay, mod out. That's over here. Okay, and then this is going to feed back here. So what this path is, this is called a swallow circuit. So it's going to swallow one falling edge, right? This is going to swallow one falling edge. Just 1 second. Okay, let's continue. Okay, so this is a 2x3 cell. Okay, so this is a swallow circuit. So when mod in is high and P is also high, when both are high, then this is going to be disabled. So the circuit is going to stop the T flip-flop from toggling. So if this input is high, then this T flip-flop will toggle and divide the frequency to half. But if this swallow signal comes in here as 0, then this is not going to toggle. So it's going to swallow one falling edge. So that's equivalent to divide by 3. Okay, so T flip-flop is for divide by 2, and T with the feedback path through a swallow circuit is a divide by 3. So this is a 2x3 cell. So let's make a symbol for this 2x3 cell. Okay, new symbol. Again, I want to make a small symbol so that in circuit it looks nice. So what do I want? I want clock and clock bar. Okay, and then I have Q and Q bar. Correct? And then I have got modulation in, and then I have modulation out. Right, and I can lower this distance slightly, move this up a bit, doesn't matter. And this is your P. Did I miss something? I missed a ground, isn't it? Okay, don't worry. So let's check this cell. Schematic. Yes, so I forgot a ground, though it is labeled everywhere. So I'll introduce another pin, which is P9 as a ground. Okay, and I will name this as GND. Okay, so I'm going to save this and close this one, and I'm going to create another pin which is GND. So I'll just copy this pin, and this is pin number 9. I'll call this as GND, and the text here, I'm going to alter the text over here to be a GND. Right, so now I have a ground pin, correct? And I have a P input, and I have a VDD. Correct, so let's just draw a box around it. Okay, so kind of slightly asymmetric, but I don't care now. Okay, another, to remind me that this is clock and clock bar, I'm going to put a small bubble here. Right, so I'm going to copy this, and I'm going to put a small bubble so that I know this is a bar. So that's the small bubble which goes in here. Right, so this is a symbol for 2x3 cell. It's okay. Okay, so that's the symbol for 2x3 cell. I am going to test this cell, because if I make a MMFD and the cells is not working, then this is not right. So I'm going to say test, sorry, test cell 2 by 3. Create. Okay, here I want a 2 by 3 cell. That's fair. And I need a supply. So let me just check something. Let me check the mux. So that's all connected. Sorry. Okay, so I am going to put certain loading. Lump components, lumped. Okay, I'm going to put some loading on the output stage. So that's a Q. That's a Q bar. Right, so this is 5 femto. And this is 5 femto. Now, coming back to what frequency will I operate it at? Okay. Coming to what frequency I will operate this at. So we know that I know that I'm designing this for Wi-Fi 6, and that Wi-Fi 6 extended band is 5.85 to 7.15. Correct? So let's look at the max frequency as 7.15. So I need to generate 2/3 of that, because we have an output stage for quadrature. 7.15 divided by 3 multiplied by 2. So I have to generate 4.8 gigahertz. So I must operate this at 5 gigahertz or above for having some margin. Actually, it will go up to 6 gigahertz, so that's okay. And then I should also have a mod out. So here I am going to put here a mod out. Okay, so this will be used for cascading, right? And then I am going to have ground. So sources frequency domain, I'm going to have supply, which is 1.5 volts, right? 1.5 volts as a supply. And then I am going to have a ground. And then I am going to have a clock. Okay, so I am going to use a pulse for a clock. So this is going to go peak value as 1.5, and this is going to operate at 5 gigahertz. 0.2 is the period, so 0.1 is the half period or the width, and so the rise time is 1 picosecond, fall time is 1 picosecond. So this is your clock, and then I need to have a clock bar. Right, so let's do that clock bar over here. Okay, and all I have to do is to introduce a delay of 0.1, half the width, so that now they will be a differential signal. Okay, so I am going to put in a differential clock in. So this will be called the clock, and this will be called a clock bar. Correct? Now, okay, so I am going to put in here transient simulation. Let me see. I'm going to put here transient simulation. Before that, I need to put the include file. So that's the include file. And you remember subbang? Subbang has to be grounded. So I am going to use this component for establishing a ground, and this tie would be called subbang. Okay, so I'm going to call this tie as subbang. Okay, so that would take care of that global node in all the gates. And then I am going to have just okay, so now here I am going to put in here mod in and p. So I'm just gonna copy this guy, mod in. Let's move it to the side so that I can put another source here. So that's p, and that's mod in. So let's put a very low frequency here. So this time period I'm going to make 6432. So I'm going to make this as 3 3.11199. So that is 33.2 nanosecond. So the corresponding frequency is going to be 0.15615625. Correct. And then I'm going to half this over here. So half of 15625 would be 0.078125. 785, and its time period is going to be 6.4 microsecond, or it is going to be 6.399 with a rise time of 1 picosecond, right? So having done that, let's just label these nodes quickly. So this is going to be P, and this one is going to be mod in. Correct? And I'm going to simulate for 12.8, 6.4, so 12.8. So I'm going to simulate for 12.8 nanosecond. So I'm going to go to simulation transient, 12.8 nanosecond, 12.8 nanosecond, steps of 1 picosecond, right? That's the maximum time step as the rise time. That's done. Okay, so this is a 2x3 cell which I'm going to test. So let's simulate this. Okay, so the next step would be cascading these 2x3 cells to make a 5/6 MMFD, or multi-modulus frequency divider. So if this works, I'm going to do that. Unless I have done a blunder somewhere, a silly mistake, this should work. Okay, almost done. So simulation is done. First I'm going to see what the clock and clock bar look like. Clock and clock bar. Okay, so they are in tandem or not? So they are. Okay, so this is clock, this is clock bar. Fine. The next thing I want to put here is going to be just repeating this graph over here. Okay, and this one I will put as P. So that's a P. You can't see it, but I'm going to make it bigger. So that's a P. And then what I'm going to put here is going to be mod in, modulation in. So that's your mod in. I'm going to move short dash. Okay, so one more thing I can do is for visibility. Okay, so now I've generated all the four states for mod in and P. And when P and mod in both are high, the circuit should divide the frequency by 3. And for all other cases, it should divide by 2. So let's just copy this and look at Q. So let's make this as Q. And let's make this as Q bar, QB. So they are in tandem, so I can remove QB. Okay, so I can delete QB. Okay, so let's look at this one. So this is kind of very thick. Okay, so let's see clock on top of it. Okay, so with this falling edge, I have a transition. So 1 cycle, 2 cycle, and 3 cycles. So this is the third falling edge. Again, I have a transition. So 1 cycle here is 3 cycles of clock. So when P is high and mod in is high, this is 3 cycles. When P is anything else, P and Q, either of the path, then the swallow is disabled, and then there is a divide by 2. So on the falling edge you have, so let's go here. On the falling edge over here, so 1 cycle and 2 cycle. So there's a divide by 2 when both are not high. When both are high, this is divide by 3. So 2 by 3 cell is working. So once I have done that, I am going to cascade them to make a multi-modulus divider. So just 1 second. So I'm going to just save this and close this. So the next step would be a multi-modulus divider. So I'm going to make a new schematic, MMFD 5_6. And the reason I'm doing 5-bit / 6-bit is because I want a larger range for choice of crystal, right? So crystal frequency, right? So all I need is 2 by 3 cells, right? Okay, so I need 2 by 3 cells. And with the first one, I'm going to do some trick, and the remaining are going to be simple. 1, 2, 3, 4, and 5. Okay, so let's select all of them, and let's put their text over here, or rather here. Either way it works. Okay, first thing first, VDD. Okay, so that's a VDD, and then I need the ground so that I don't forget there is a ground here. So that's a ground, and let's connect them. So this is VDD node, so everything is VDD here, right? So this is VDD. Okay, and then this is ground. Right, fine. And mod in over here is VDD because I'm not going to disable. Do I want to disable MMFD under any situations? It might be when you go into standby. Okay, so what I'm going to do is I am going to put here an enable pin. Enable pin. So that's an enable pin. Okay, so if this is held high, then the entire MMFD would be enabled. So let's just cascade them. Okay, and then this one is going to be Q. So this one is going to be Q output, and then there is a Q bar output. Right, nothing special in here. Okay, and then these bits, okay, I am going to put through mux. Okay, so I am going to take in a mux here, which is over here, and I'm going to rotate that mux. So in that mux, so this is my P input. Okay, so in this case, if this is 0, so this is your select. Okay, fine. And this is, let's say, so I'm going to put here VDD in ground. So this is going to be VDD, and this is going to be ground. Correct? And F5, that's your text. Okay, so I'm going to repeat this, and this I'm going to say select. So I'm going to select either it is a 6-bit or a 5-bit. So I am going to put here this, call it select. Correct, and I'm going to repeat this. 2, 3, 4, 5, 6, and then I am going to have, okay, I am going to have this as a grounded, and I am going to now put the pins C02, so I'm going to have C0, okay, C0, C1, C2, C3, C4. So when select is low, I'm going to use this 5 bits, and these are going to be cascaded, mod in and mod out. They will ripple, and even over here they will ripple. Okay, and this mod out is of no significance, so I will just leave it floating, or for name's sake I am going to just put a small capacitance there. Lump components, basic components. Okay, so that's a mod out for the entire thing. Okay, so really I'm not interested in this 5M2, so I'll just leave that track open, but I don't want simulator to complain, that's why I have put a 5 nano. Okay, now I'm going to have one more pin here, which is going to be C5. Right, okay, let's put it this way. C5. Okay, and I'm going to mux them. So when I use 6-bit, all these would shift to the left. Okay, so basically this would shift to the left. So now the 6 bits are applied now. Correct? Okay, so this being said, all I have to do is clock and this will come from the VCO, right? Clock and clock bar, and this will be the divided output. So I am going to put here clock, right, and a clock bar. Okay, so I'm going to have a clock and a clock bar. Now I'm going to use a mux again. So I'm going to copy this one and rotate it out. So I'm going to put two of them. Okay, so now what these are going to do, so just 1 second. Okay, so when select is low, then, so is there a ground? Yeah, so this I don't want. Okay, so these are okay, right? Okay, so now this would be the clock. So when 0 is there, okay, and this output, so this is Q bar or clock bar here for cascading, and this is going to be the clock. So this is done. And when this was there, when select is high, then its output would go to here. Okay, so I have generated, I'm either using a 5-bit when select is high. When select is low, I'm using 5-bit, and my first bit is going to be this one. So this is going to be C0, C1, C2, C3, C4. Now when select is low, then this clock is diverted to clock here and clock bar here. And when select is high, then its output is going to be cascaded over here, and this will receive the input. And in this case, the C0 will be over here because select is high, and C1, C2, C3, C4, C5. So this is going to be a 6-bit. So depending on the select, so I'm going to make another pin which I call as select, and I will name this as cell. Okay, so this is my multi-modulus frequency divider. So have I missed anything? So enable has to be held high for this divider to work. Otherwise, this is not going to work. Yeah, it's going to hold the state. Okay, so now I'm going to make a symbol for this one. New symbol. And again, I want to keep it as small as possible. So I'm going to first rotate this. And this is enable. Okay, and the ground has to be here. So this is enable. So I'm going to rotate this. So this will enable it. Then I need a VDD. Oh, wait, VDD over here. So that's okay. So there will be enable and VDD. And then I need a ground. Ground needs to be below. So that's a ground. Then I need clock and clock bar. So that's a clock and clock bar input. So as I'm going to use this in feedback, right? So I'll put it on the right hand side, isn't it? Yeah, I'll put it on the right hand side. Okay, so this will come from the VCO. And then you have a Q and Q bar, which will be going to the PFD. What? Q and Q bar. Huh? Just 1 second. This is what? This is Q. Cancel. Fine. This is Q and Q bar. And this is the select input. Okay, so let's remove this. Just 1 second. Bear with me. Let's make this smaller. This is clock and clock bar. This is whether this is 5 or 6. And this is going to be your enable. Okay, so this is your 5x6 multi-modulus divider. So I'm going to just put a small text so that it reminds me what that is. And I'm going to put here a bubble so as to remind me that this is a inverted input. Right, so let me just do this. And here, let me copy this over here. And let me make a small bubble here. And let me put a small text also. Insert text. So I will call this as MMFD. And this will be 5/6. So that's that. And I have to put a bubble here. Come on. Okay. So slightly bigger. Oh. Okay. Fine. So this is your multi-modulus frequency divider, and I'm going to check that. Okay, so to test that, I'm going to make a new schematic and say call it test MMFD. Right, create schematic, put that over here, and give it a supply and a ground. So that's a ground, and then there is a supply. I can copy this from test 2x3 cell. So I need a supply. I need this, I need this, I need this. Probably I need these also. And I need this 5 gigahertz input. Isn't it? Yes. Control C. Cancel it out. Control V. Oh, after you close it, you cannot. Okay. So again, I need this. I need these. I don't need this label, this, and I need this. Control C. And you shouldn't close this because it doesn't do that. It doesn't. Control C, Control V. Okay, so all the things are over here. So first thing first, I'm going to connect the clock. So this is clock input and this is a clock bar input. Clock input, clock bar. So let's label them. So this is going to be clock. And this is going to be clock bar. Correct? So this is done. Then this is my output over here. Correct? So these are my outputs. So this is Q bar and this is Q. So all I do is this is Q and this is going to be Q bar. Right, and then I need a supply which I didn't copy. So I'll just copy this supply, Control C, Control V. So that's my supply, and enable is high because I'm testing this, so that's tied to VDD. Okay, and what I'll do is I will create two control voltages. Okay, so 1 and 2. So one of them is 0 volts, which I will call as 0. Other one is 1, which I'll call as capital O, 1. And I'm going to have everything as 0. Okay, so then it is going to divide by 32. Okay, and this is going to divide by 32. So what I'm going to do is I'm ready for simulation. Transient, and I need to simulate for 20 nanosecond maybe. Yeah, 20 nanosecond. Okay, done. So I'm ready for this simulation. So let's see, everything is okay. Clock bar, all inputs are Z. This is output, this is supply, this is ground. Everything is okay over here. Inside here everything is okay, looks to me okay. And everything is okay. Yeah, everything is okay. This is select, this is select. When select is 0, this is grounded, that's okay. This goes here, so this is C0 to C4, so that's fine. To me everything looks okay unless I goof up. So I'm going to hit simulate here. Okay, so I'm going to put you to pause while this simulate takes place. Okay, so what I have plotted is just finish simulation. I have plotted clock bar, but here I plotted Q and clock, and this is one cycle, and I'm going to count the pulses. So this is a falling edge, so I'm going to count 1. So 1 is over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and 32. Again, 1, 2, 3, 4. So this is dividing by 32. Let's check the other extreme. The other extreme is going to be all this is 1. Okay, so I am going to name this node as 1. So now the divide would be 63. Okay, so now I'm going to hit simulate again, and I'm going to put you on pause again. Okay, so while this simulation goes on. Okay, so let me put you on. Okay, so now the simulation is finished. So let's count that. This is falling edge. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, and 63. Right? So now this is divided by 63. Okay, so this cycle is divided by 63. Now I'll run one more, which is going to be checking the higher side of it, which is your 6-bit. So in that case, I'll make this one as 1 and remaining as zeros. So now it will be dividing by 64. Okay, so name Z Z Z Z Z Z. Okay, so I'm going to hit simulate on this one, and I'll put you to pause. Okay, simulation is complete. So now here, this is going to be a 64 division. Okay, so similarly, I can look at all ones as 127. So I have counted this to be 64. I can count this to be 127. This is a needless exercise. Okay, so that means that I have designed a multi-modulus frequency divider, which can divide anywhere between 32 to 127 depending on the select line. But the only caution here is don't choose a crystal such that you are going to have overlapping ranges, because for that I haven't done any arrangement, right? So either you choose a crystal which results in frequencies so that the crystal lies between 32 and 63, or between 64 and 127. Don't have overlapping region between 5 and 6-bit. I haven't designed for that logic. Okay, so this completes our exercise on first component design, which is multi-modulus frequency divider for fractional and PLL. The next thing which I'm going to design is a mesh 111 all digital sigma delta modulator, which is going to be a third order sigma delta modulator. So I'm going to sign out now. Thanks a lot. Thank you.